Bohr's model for the atom was a huge improvement on our model of understanding the atom, but it was clearly missing something. So the most intuitive improvement in our understanding comes from de Broglie. He found that all matter has a wavelength, and well, he kind of hypothesized it, and that wavelength corresponds to Planck's constant divided by the momentum of the object. So if an object has a momentum of, that corresponds to a few meters per second, and a kilogram or, tenth of a kilogram, in our everyday experience, this wavelength is so small that it is undetectable. But on the scale of an atom, this de Broglie wavelength is on the order of the scale of the radius of that atom. Notice, the faster the object goes, the shorter the wavelength, right? So the momentum increases if it's going faster, so that causes the wavelength to get shorter. So it's kind of like light. So the shorter the wavelength, the higher the energy. So how does this explain the energy levels of an atom? Well, as an electron orbits the nucleus, it has a wavelength, and that wave cannot destructively interfere with itself. It is kind of like the wave on a string problem that we did back in 201. The wavelength of the electron needs to correspond to the circumference of the orbit, which is 2 pi times the radius. From this, we can solve for the angular momentum, and we find that the angular momentum is a harmonic, or a quantum number n, times h bar, which is Planck's constant divided by 2 pi. This is exactly what Bohr proposed for his model of the atom. So, the origin of the stable orbit in atoms is that the lowest possible orbit is one that undergoes one wavelength around one orbit. The electron can't crash into the nucleus because it is stuck in its energy state, and it can't go to a lower energy state. The next strong piece of evidence for the wave properties of matter is that if we do a two-slit experiment with electrons, we can see an interference pattern. So we've studied this before with light, so the shorter the wavelength of light, the closer together the fringes. So the same thing happens with electrons. If we accelerate a beam of electrons, then the wavelength gets smaller and the fringes move closer together. If they slow down, then the fringes move further apart. This is just like light. The one thing that drives people crazy about this result is that you can slow down the rate of the electrons, so how many electrons, so only one electron is going through the slit at a time. So if you only have one electron, then you'd think that the interference would go away. But it doesn't. The wave nature of the particle interferes with itself, so you still get an interference pattern. This is one of the things that bothers people about quantum physics. The particles act like a wave until it is observed, so when it hits the detector, it has a precise position. But before that, it acts like a wave. This result bothers people a good bit, but it is a consequence of the wave nature of the particle. If it is a wave, it doesn't have a precise position. This leads to effects that are unintuitive when thinking about particles, but make sense when thinking about waves. So, there are other quantum numbers other than n, so things like the angular momentum, the direction of the angular momentum, and the spin, that leads to the periodic table, but I think I will leave that to the chemists to explain. In any case, I hope this gives you kind of a bird's eye view of what happens as we go to very small sizes. Particles have a wavelength that, when things are small enough, becomes critical for explaining the physics at the atomic and subatomic scale. Okay, so I think that gives you the idea here of quantum physics. So this ends the online classwork part of Physics 202. So you have a few questions here to answer, so good luck with your questions, and take care of yourselves.